Hello everyone. I present today my presentation titled by NanoCarbon in ultra-high performance concrete. This work was done by Nancy Soliman, Ahmed Amran, Danielle Gracious, and Beige Martini. So I will start my presentation because all of us, maybe we know all this story. So according to the IPCC 2021, that we have to overcome the problem of CO2 emission. So we have, or we keep the temperature like below 1.5 degree. We have to reduce the CO2 emission by 2020, by 2030 by 40%, and reach to net zero by 2050. And actually, a lot of the countries has been committed to have a reduction, or like to reach to net zero 2050 by 2050. So USA has joined and committed to reduce or reach net zero goal by 2050. However, we face another problem. So according to United Nations forecast that by 2050, up to 2/3 of the people will live in urban area. So by that, we need more urbanization areas such as tunnels, bridges, infrastructure to keep this urbanization. So we have a big stress from the CO2 emission, like reduction CO2 emission by 2050, and also we have to have more urbanization in infrastructure. So concrete, one of the most widely material for infrastructure. So for example, in USA, we have 10 billion over 500 ton in USA and 10 billion in worldwide. And the concrete is the most material in the world because the concrete compared to the steel and the glass fiber, if you can, all of us, we know this graph, according to the glass or bitumen or the composite material or steel, the concrete has low embedded energy and low CO2 emission compared to the other material. So if you'll see here in this graph, here is the most of the construction material, and we can see the approximately 50% of the construction material that's fabricated from cementitious material. However, the traditional strength paradigm has been shown three main flaws, eco-efficient, as the production of the concrete contribute up to 8% of CO2 emission worldwide. So another point is durability issues, as for example, 40% of the bridge in United States require rehabilitation of $28 billion by the year, and this is due to also the climate change, more hurricanes, more floods, and so on, and also functionality issues. So the concrete has negative entropy, so cannot has negative entropy through matter or energy or any external stimuli. So whatever the concrete has subjected to load, change in the moisture, a change in the chemical compound, cannot have any external stimuli. So the concrete is not a smart functionalities. So ultra-high performance concrete has been developed to overcome one of the more deficiencies of normal concrete. Why? Because the UHPC consists of ultra-high strength, high ductility, and excellent durability. And the UHPC consists of cement, quartz sand, huge amount of silica fume, quartz material without no coarse aggregate. And why the UHPC has been developed to overcome deficiencies of normal concrete? Because the UHPC can be used as a normal concrete, but without any passive reinforcement. Also, we can reduce the structural member of UHPC up to 70%, and this also can be considered as a sustainability and low cost of the material and self-weight of the material. Also, the UHPC has superior durability, so it can be longer surface and reduce maintenance cost compared to the normal concrete. However, also not only good mechanical performance and durability, but also UHPC has a biggest problem, as the UHPC fabricated with approximately up to 1,000 tons of the cement, which can require high energy, consume natural resource, and also can be contribute in the greenhouse gases. Also, large amount of crystalline material can be high cost, consume natural resource, and it can be also of problem of can cause cancer of the human. Also, UHPC fabricated with huge amount of silica fume, which can be also has the biggest problem in rheology, shrinkage, and also increasing the cost. A lot of the researchers have been started to overcome the problem of the UHPC by replacing traditional component by supplementary cementitious material. And in Sherbrooke, we developed even a novel ultra-high performance concrete where we can reduce the CO2 emission and even enhancing the strength compared to the traditional one that fabricated with the limestone filler, fly ash, or slag compared to the traditional one. However, also, we have a biggest problem due to the climate change. The concrete has also, the UHPC still doesn't achieve a good smart functionality. Especially with the winter, for example, come with the threat of icy road. So we need like the highway become like more deadly. So for example, in Iowa, 40 key vehicles have a big injury and causing a multi-injury in 2021 due to removing the snow. Not only that, to remove the snow, we have to add some salt. And from removing the salt, we can have a lot of contaminated water. We can also have a biggest problem that the concrete UHPC doesn't have a self-sensing capacity. And by that, we can have we cannot even avoid sudden collapse on structural integrity. So the question, can UHPC be sustainable or adding sustainability in UHPC by improving a new functionality? Yes. In Texas A&M at Corpus Christi, we developed a novel and nano-modified electron conductive ultra-high performance concrete. And the idea here is to construct multi-layer of conductive material through replacing silica fume by electron NanoCarbon black material, especially that the silica fume consists of 25% of silica fume from the cement addition, which is approximately 250 kilogram per meter cubic. And the role of silica fume in UHPC as the pozzolanic material and as a filler effect. So what about to replace the part of the filler material, of the role of silica fume as the filler material by material with adding a new functionality to the system. The other part, cement and the quartz part, we're gonna replace the partial cement and the partial amount of quartz powder by using waste copper material. And also by that, we're gonna achieve different multi-way of the conductive material through quantum tunneling conduction introduced by NanoCarbon black material, conduction facilitated by the waste copper material, and also UHPC has a steel fiber. So we can develop different paths of electron conductive material. But we have three main questions. UHPC is highly heterogeneous material that fabricated with huge amount of the powder. And this powder is hydrophilic material. So, however, the carbon black is hydrophobic material, has tendency to agglomerate. So the first question in the research proposal, what is the dispersion mechanism of hydrophobic material such as NanoCarbon black into a complex ultra-high performance matrix? And how this can impact the durability, how can this impact the electrical properties and the strength capacity of the composite? The second point, the UHPC consists also of heterogeneous material. And the UHPC, fabricated with blue stoichiometric level with less than 0.25. So the question, how the different ratio of the conductor insulator composite, water cement ratio, volume of cement, volume of aggregate, and the nano and the microfunctional materials that consist of the carbon black and the waste copper can impact the electrical Joule effect, self-sensing, and what is their interrelation. The third question, how does the formation of electron conductive of the volumetric wiring from NanoCarbon black material, steel fiber, waste copper can impact the macromechanical characterization and the microstructure investigation? So to answer this question, we made a primary investigation about depolated ultra-high performance concrete by using NanoCarbon black volume fraction. And in this graph, we can see NanoCarbon black volume fraction versus electrical conductivity of ultra-high performance concrete. And the inset side we can see in the upper, this is the resistivity of UHPC, and the inset file, this is the relation between the volume fraction of the carbon black minus the volume fraction of the carbon black at percolation threshold versus electrical conductivity. And what we observed here, that the addition of carbon black led to enhance the electrical conductivity by form a percolation threshold at 2%. and also what we observe it, we reached saturation point above 60% of nanocarbon black. And what we observe it here, that the exponent of T, which is equal 1.66, this is the inset related to the conducting phase geometry. When we have a higher value of this conducting phase, it means that we have a tortoise of the nanocarbon black in the UHPC matrix. To understand the effect of the nanocarbon black, and even in the future with the waste copper, in the macromechanical characterization, we use the chemomechanical multiscale approach, where we have the variable of the UHPC with a different water binder ratio, like 0.25 and 0.3, and the nanocarbon black range from 0 to 10%. We measure the conductivity, porosity, and the mechanical and the microstructure characteristic. At macro scale, we measure the compressive strength, tensile strength. At micro scale, we measure the micro indentation modulus, hardness, and the indentation modulus. Micro scratching via fracture toughness via micro scratching test. And at nanoscale, we measure the hardness and the indentation modulus using a nano indentation technique. To link between this scale from hardness and the compressive strength, we can obtain the cohesion and deflection coefficient of the material, and from the relationship between fracture toughness and the indentation modulus, we can obtain the fracture energy, and from fracture toughness and the indentation modulus, we can obtain the fracture processing zone, which represent a ductility of the material. And from nano indentation, we can obtain, using the micromechanics model that developed by the Olm and the co-worker, we can obtain the backing density of the CSH. So here I will present just only one of the parts about what is the impact of the addition of nanocarbon black as the replacement of the silica fume, to about the macromechanical characterization for the water binder ratio 0.25. And what we observe it here, that the addition of nanocarbon black led to a big reduction in the compressive strength, however, a slight reduction in the tensile strength. And the reduction of the compressive strength is highly compared to the reduction in the tensile strength. So fracture toughness via scratch technique, here the fracture toughness can be obtained from the scratch test, and from a scratch test we can obtain it we're using the linear elastic model that developed by the Franz Olm and the co-worker. We can estimate the fracture energy. From fracture energy, we can estimate the fracture toughness that can be related to the quality of the binder. And the fracture toughness represented about the ability of the material to withstand in the front of the crack. And from here, we can observe it, that the addition of nanocarbon black lead to increase the fracture toughness and improve the fracture energy that can be originated from the crack deflection of the material, where the nanocarbon black can be considered as the obstacle in the front of the crack. And this SEM graph, and I obtained it before in my work in the pure cement paste at MIT, where we can see the crack deflection of nanocarbon black when we integrate it in the cement matrix, which confirm our result that the addition of nanocarbon black as a silica fume, the synergetic effect between nanocarbon black and silica fume can lead to enhance the fracture toughness of the material due to the crack deflection. The ductility, we estimated the ductility from the relationship between indentation modulus and the indentation hardness that developed by Franz and the co-worker at Franz and the co-worker, and the relationship between indentation modulus and the indentation hardness can be considered as a competition between plastic dissipation and the elastic energy storage, which can represent about the ductility of the material. So, and also it can be estimated from the fracture processing zone, where we can estimate the fracture toughness divided by the hardness and squared. And this can be a zone in the front of the material, where can represent can be a head in the crack tip, where the stress decrease from far field stress to the field stress. And it can represent, if this fracture processing zone is high, it means the material is ductile. If the fracture processing zone is small, it means the material is brittle. So from the addition of the nanocarbon black, we can see that there is a reduction in the M&H ratio and the fracture processing zone. So as a conclusion here, the addition of nanocarbon black reduce the ductility and the fracture processing zone, and this can be related to the plastic dissipation capacity that can be introduced by fracture processing zone. So discussion question. So now we need to understand why the addition of nanocarbon black in ultra high performance concrete lead to increase the fracture toughness decrease the macromechanical strength, compressive strength, and tensile strength, and decrease the ductility. To go through, we estimated the cohesion and the friction coefficient, the two parameters that can represent the strength, the quality of the strength of the material. How we can estimate friction coefficient? We can estimate it according to the Franz and the co-worker by a relationship between compressive strength and hardness. And we can estimate the cohesion as the relationship between compressive strength and the friction coefficient. And what we observed here is that the addition of nanocarbon black led to enhance the friction coefficient, and this can give us proof that the addition of nanocarbon black can replace partial amount of the silica fume. However, the addition of nanocarbon black leads to the decohesion in the matrix. And the decohesion in the matrix the friction enhancement, it can be dominant compared to the decohesion, and this is why we have the answer of our question, why the addition of nanocarbon black lead to the reduction in macromechanical characteristic of ultra-high performance concrete due to the decohesion of the matrix between the nanocarbon black and cement matrix of UHPC. To know what is the reason of the macroscopic decohesion of the material, we measure only the indentation modulus and the indentation hardness for the first cluster of ultra-high performance concrete. And what we observed here is that the addition of nanocarbon black led to a big reduction of indentation hardness from the cluster 1 of ultra-high performance concrete, and also the indentation modulus of the cluster 1 of ultra-high performance concrete. So by that, we have the reduction of this, like indentation modulus and the indentation hardness is the answer why we have the decohesion and why we have a macromechanical structure, reduction in the strength. So now we need to understand why the reduction of the hardness and the stiffness from the nanoscale. This can be for the next step, where first we can unveiling the nanomechanical signature of ultra-high performance concrete by continue estimating what will be the impact of the backing density of the CSH, and also we will continue our work about dispersion using surface functionality and the synergetic between chemical and physical technique, and also we will investigate the application of electron conductive ability with the self-sensing capacity and for structural health monitoring and the self-heating capacity for improving the infrastructure ability. So the conclusion, the addition of nanocarbon black led to enhance electrical conductivity of ultra-high performance concrete, led to enhance the friction at macro scale. However, like due to the filling the micropore, and by that it can substitute the role of silica fume as the filler effect of the silica fume, of ultra-high performance concrete. However, we have the decohesion. This decohesion resulted from the reduction of the CSH at nanoscale. So thank you.
Good work. I have a couple of questions, not one question. What sand particle size you have maximum sand particle size?
In
your UHPC, in your UHPC mixture, what is the maximum size of sand?
Maximum size is 600 micrometer.
Oh, that means passing through ASTM number 30, that's one question. Can you go to the slide on compressive strength versus your nano black percentages? Yeah. It appears to me that you got a maximum compressive strength of around 110 megapascals, right?
117 MB.
117, so which is not a UHPC.
No, it's UHPC. UHPC can be defined by 120 MB.
120 megapascals, I know. You have not reached even minimum 120 megapascals.
Yeah, but this is 117, so plus or minus.
Of course, we are getting more than 120 megapascals. You have not even reached minimum strength, 120 megapascals to classify as UHPC. Whereas the composition may be okay. Why you have got such a low compressive strength for a UHPC?
Yeah.
117 is low, definitely, for sure, because 120 is minimum, 117 we call it as low. But why you have not achieved greater than 120? Because we are getting 160, 170 megapascals.
Yeah, actually, yes. According even to my paper, even under my patent in ultra-high performance glass concrete, we achieved strength 230. Because I believe that the carbon black, it is very hydrophobic material and has tendency to agglomerate. And we started by the low water cement ratio, blue, water bind ratio 0.25, but however, we couldn't able to make concrete. So this is why, at the water bind ratio 0.25 and 0.2 and 0.17. So to trade off between compressive strength, mechanical performance, and the electrical properties, this is why we go through the highest water binder ratio in ultra high performance concrete, which is 0.25. However, in the future, if we're going to find a good surface functionality of the carbon black material without to reduce, maybe tomorrow you can attend the presentation of the dispersion of nanocarbon black, because like the problem, if we're going to disperse the nanocarbon black, we lose the electrical conductivity.
Yeah, I was wondering, because even at 0% nanocarbon black, your strength is only 117 megapascals, right? That's control mix, 0% means.
But these, yes, okay,
so that's one thing. Second thing, you have given a good reason for decohesion between the compressive strength and the toughness values, because toughness is increasing, compressive strength is decreasing, which is surprising. My take on that is...
because this is a crank deflection.
Yeah, so my take on that is two things. One is you can control the fiber orientation by controlling the rheology of the paste. That way, I'm guessing that is because of the deorientation of steel fibers.
Yes.
That is one point.
No steel fiber here.
No steel fiber here?
No steel
it's
fiber.
only plain?
Yeah, it's plain. It's
Okay,
just only
I thought it's a fiber reinforced UHPC mix. So basically rheology, if you can control, I think you may get a better...
This is why I was telling you we have to work in the dispersion of surface functionality of nanocarbon black. By that we can integrate nanocarbon black without the biggest problem.
By the way, what is the particle size of your nanocarbon black?
Like 30 to 50 nanometers.
Okay, thank you.
You're welcome. Yeah.
I'm Konstantin Sobolev, University of Wisconsin-Milwaukee. So yes, shows that you have this volume fraction of total volume, or it's silica fume replacement, or...
This is silica fume replacement.
Silica fume replacement.
Yeah.
So, and what was the total of silica fume content?
Like 25%.
25%. So very small portion of silica fume was replaced by carbon black, nanocarbon black. You mentioned about the particle sizes, but also what is the morphology of the nanocarbon black? Is it porous material?
Porous material.
And yes, so so it leads to another question: how you counted for porosity? Because did it include like embedded air inside of the particle and inside of the matrix?
I didn't measure the porosity actually of ultra high performance concrete. It's just only...
No, but for nanoparticles themselves, if they are porous,
yes, porous.
so I think you need to understand, like, if, of course they are hydrophobic, so water is not really absorbed inside, they are not consumed like lightweight aggregate type of thing. But I think you still need to report on the porosity of individual nanoparticles. You still need to present what is the morphology, maybe TEM pictures, etc. So this would add up to your study.
Yeah, that's perfect.
Thank you.
Thank you so much for the guidance.
Thank you very much. Any other questions?
Thank you. Bye.